Okay, so in this movie clip, we're going to learn the contents introduced in chapter 11. So the outline of lecture note number 2 for BJT is this: ideal transistor analysis and narrow base, narrow emitter, and it was small model, which is kind of a current voltage characteristic for BJT. And what if the base width has been modified and modulated? Then what kind of things would be happened? I mean, the how does collector current has been affected by very narrow base? That kind of stuff. But if you're very familiar with the MOSFET, I guess the base width modulation is almost corresponding to the channel length modulation in MOSFET. Okay, so base width modulation, physical event happened in BJT, denoted as base width modulation, is almost identical to the channel length modulation happened in MOSFET, very short channel MOSFET. Okay, so let's move forward. So first of all, before moving forward, let's summarize the notation in PMP BJT. So on this figure shows a cross-sectional view of P plus NP BJT device, emitter-based collector, and as we have used the axis indicates the how to say the injected carriers. So axis indicates the direction for injected carriers. So in this case, the hole can be injected into the base, and this hole would be diffused along x direction. Okay, so this origin point is corresponding to the depletion layer edge of emitter base junction. Okay, and this edge is denoted as W. So again, as I have explained you, W indicates uh, the base width of not physical, but just a base width of the quasi-neutral regime of base. Okay, the physical width of base would be this. Okay, from here to here. So including the depletion layer width, we can use a WB. But if I use a W, that indicates the width of the quasi-neutral base regime. Okay, so again, the x prime, x2 prime, those stuff can be defined like that. Because always think about how to define the x2 prime and how to define the x1 prime. Think about how the injected carriers are diffused. Now electron is injected here and it's going to move in this x prime direction. And once the electron has been injected into the P plus emitter region, and if this electron would be diffused along x2 prime direction. Okay. Okay. And now let's move on to the second part of this lecture note. N sub E, D sub E, tau sub E, L sub E stuff. What is this? Yes, doping concentration in emitter. But since this is a PNP BJT, so emitter is p-type. So p-type is acceptor, right? So N sub A, acceptor concentration in the emitter region. So NAE, okay, NAE is simply denoted as N sub E. Okay, so emitter concentration indicates the majority carriers, concentration. Okay, NE indicates how much acceptor has been doped into this emitter regime. What about the DE? DE is an emitter, no, the diffusion constant in the emitter region. But diffusion constant of electrons or holes? That's the question. In PN junction diode theory, you may remember this. PN junction diode is named as minority carrier device. MS diode, metal semiconductor diode or Schottky diode, MS junction diode is named as majority carrier device. Why is that? If you're not familiar with the MS diode, just forget it. PN diode, we have learned it. In PN diode, holes are injected into the N side and electrons are injected into the P side. Take a look at this combination. Under forward bias, right? Under forward bias, how those electrons and how those holes are moving. That movement would determine the diode current. So minority carrier is kind of main actor or actress. Okay, so DE, electron, no. The diffusion constant in the emitter region would be mainly determined by diffusion constant of minority carriers in the emitter. But what is the minority carriers in the emitter? Yes, electron. So I have used the N. So the lifetime in the emitter region is mainly determined by lifetime of electron. Electron is minority carrier in emitter. Okay, and Le is Ln. So everything is very simple. Please remember that when we are talking about the d tau L, think about the minority carriers d tau L. What about the doping concentration N sub E? Always think about what type has been used for this emitter side. Okay? And now let's take a look at the last line. N sub E naught. What is this? N is electron concentration. Naught is atomic equilibrium. E indicates the emitter. So electron concentration in the emitter, atomic equilibrium. So emitter is, p-type, equilibrium state and electron concentration. Okay. So electron concentration in the p-type material, atomic equilibrium. How to write the equation? You can use mass action law. Electron concentration times hole concentration in the same material, p-type, thermal equilibrium, okay, pp naught. So those two terms, multiplication of those two terms is equal to what? Yes, Ni square. Okay, but what about this? pp naught. pp naught is identical to the N sub E. That is N sub A in the emitter region, right? NAE. Okay, so you can write down this. So Ne naught is Ni square over Ne. So please repeat this work for base and collector. Everything is very simple. NB means N-type, right? So donor. D tau L is determined by minority carriers D tau L. In the N-type base material, minority carrier is whole, right? What about the last line? The atomic equilibrium in the base regime, the minority carrier whole concentration is equal to Ni squared divided by what? Yes, Nb naught. Atomic equilibrium in the base, electron concentration is fully determined by doping concentration in the base. Okay? So please take your time to do and to have the NC, DC, tau C, LC, and C naught. Okay, please have your own time to write down the right equation. Okay, now it's time to build up the game plan or strategy for current voltage derivation for PMPBGT. This game plan is quite similar to the game plan we have used for ideal PN junction diode theory or PN junction diode current voltage derivation. So there were three main steps to get the current voltage characteristic of PN junction diode. How about here? Read out the sentences in this lecture note. The very first step, number one, solve what? Minority carrier diffusion equation. Do you remember this equation? From the continuity equation, we have derived the minority carrier diffusion equation, right? And in the PN junction diode, this minority carrier diffusion equation has been set up. and derived in each side. Once the hole has been injected into the n side, so how those holes are diffused, you can have tau delta p sub n divided tau x. If we take a derivative 2 times is equal to tau sub p sub n naught l n square. So this second order differential equation has been used as minority carrier diffusion equation. For what? Yeah, for the holes in the n side. But previously we have solved this minority carrier diffusion equation for the p plus n, one-sided p-n junction. So how much a hole has been injected into the n side is a key things in determining the total current for given voltage. But herein, in the case of BJT, we need to solve 3 different minority carrier diffusion equations. Why? Because we have 3 different quasi-neutral regions in PNP BJT. Okay, in one-sided PN junction, we have this part, lightly lit up to side 1. This playground is a major one in determining the current versus voltage characteristic. But in PNP BJT device, we should solve the minority carrier diffusion equations in each quasi-neutral region. Okay, then why we are solving this second order differentiation? Yes, as described here, we would like to know the excess minority carrier profile. That means delta sub p, for example, in PNP, that is now base, right? So delta, the hole would be injected into the base. So minority carrier, which is hole, excess means delta in the p side, okay, as a function of x, because here the quasi-neutral region is 0 to x and the edge is w. So we would like to know this equation, delta p sub b as a function of x. But that's not good enough. We need 2 more excess minority carrier profiles. What is it? Delta n sub emitter side x2 prime. What about the delta p? Delta p collector side x prime. Those stuff, or delta n sub c x prime. Yeah, this kind of stuff. We'd like to know that. So let me summarize it. I guess let me draw P and P again. So this is a P emitter, and here your N-type base, and here P-type collector. So in between, we're gonna have a depletion layer here, here. Okay, and this is X, this is X prime, and this is X2 prime. If you are not familiar with why I have used the X prime, X2 prime, go back to this slide. Just herein we have defined 3 different x-axes for each quasi-neutral region. Okay, and y-axis indicates here the y-axis. All the y-axis indicates excess minority carrier profile. Okay, delta n or delta p. All right. Now this BJT, this P and P BJT is working under working in the active mode. So active mode means this emitter base junction is forward biased, and this base collector junction is reverse biased. Okay, so this BJT is in forward active mode. Okay, and now based on the knowledge for the excess minority carrier concentration in the p-n junction diode theory. Okay, so now the holes are injected into n side, and since this base width is very narrow, so go back to the narrow base p-n junction diode analysis. So delta p sub in the base side is this, is identical to the ni squared divided by n sub b times exponential emitter to base voltage difference. I mean this p and this n. When we are talking about the PN diode theory, the voltage difference was VA, but herein I would like to say emitter base voltage difference. So instead of VA, I have used the V sub EB. Okay, so exponential V sub EB over KT over Q minus 1. Okay, so this equation has been derived from the minority carrier diffusion equation in PN junction diode. Okay, so delta P sub B uh, at x of 0 is this. If you're not familiar with this equation, go back to the PN junction diode theory analysis. Then you should see this equation. Okay, and what about this portion, this part? At x2 prime is 0, the electrons would be injected into the p side, and this value delta n in the emitter is equal to what? Ni squared n sub e and exponential v emitter base divided by kT over Q thermal voltage minus 1. Okay, and here x2 prime is 0. Okay, this point. So this excess minority carrier elect, this is x when x is 0. These two initial value of excess minority carrier has been injected into the other side, and they're gonna be diffused toward the other edge of each region. So the concentration of delta n of E and the concentration of delta P sub B would be decreased. However, since this emitter side is long enough for those injected minority carriers to be diffused, I mean the total width of emitter is much wider than the diffusion length of electron. I mean the L sub E, right? But in base region, the diffusion length of hole is much longer than the uh, total width of the base, quasi-neutral base. So, as we have learned in the narrow base PN diode theory, the excess minority carrier concentration can be written as a first order polynomial equation. I mean the delta P sub B of x is ax plus b. The first order polynomial equation would be good enough to describe how much excess minority carriers has been injected. However, if the WE is much longer than the minority carriers diffusion length, then most of the excess minority carrier concentration would follow this exponential shape. Okay, so this has been well found and observed in a conventional and typical PN junction. However, if one side is designed with a very narrow base, then excess minority carrier profile would follow not the exponential equation but a first order polynomial equation as shown in here. If this sounds very complicated, please go back to the narrow base PN junction diode theory, and please go back to the ideal PN junction diode theory. You should very familiarize yourself with the two different concepts, narrow base PN diode versus typical PN junction diode. And as a game plan to derive current voltage characteristic of two different types of PN junction diode, one of which is a PN diode, the other of which is a narrow base PN diode, what was the step number one for deriving current voltage characteristic? Yes, we have always solved the minor to carry diffusion equation in each quasi-neutral region, p side and n side separately. And in the case of narrow base PN diode, the access minor to carrier profile is following and described as a single first order polynomial equation. Okay, all right. Since this emitter base junction is forward biased, so many holes can be injected into the other side and many electrons can be injected into the other side. But since this BJT is working in a forward active mode, the base collector junction is now reverse biased. So the excess minority carriers concentration would be this. That is N sub C, delta N sub C. Excess minority carrier concentration in the collector region. So delta N sub C is this. Okay, and this part would be Ni squared over N sub C times exponential V sub collector base. Yeah, collector is p-type, right? So collector base voltage difference divided by kT over Q minus 1. But since V sub CB is negative, so now this value is very small. Okay, all right. Okay, and one more thing is this part is denoted as N sub C naught, thermal equilibrium. In the collector region, the minority carriers concentration, Ni squared over N sub C. Okay. All right, and one more thing is here, this value. So this value is denoted as, let me see, Ni squared over N sub B times what? Yes, exponential width of a collector base divided by kT over Q minus 1. Okay, so this part and that part now reverse bias 1. Okay, so in PN diode is under reverse bias, and minority carriers are, diffused into the depletion layer. So the excess minority carrier concentration at the edge of the depletion layer has been defined as this and that, this and that. Okay, and again this VCV is negative, so this value is very small. I guess this value, this all of this analysis has been well trained, and I guess it's not a big harder for you to follow up the next one. Okay, that is step number one for the game plan for IV derivation, and now let's move on to the next step. Step number two. Please refresh your memory. What was the step number two in the PN junction diode IV derivation? Yes, we have solved the diffusion current for each quasi-neutral region. So here, let me write down change my color. Okay. Step number two is this. Find the minority carrier diffusion current. Okay. At depletion region edges. Okay. So I'm in the here, there, here, there. Okay. So I sub En means what? Yes, by electron in the emitter region, how much current is formed. So how much electron concentration has been, varied along x2 prime direction. Okay, so this doping concentration gradient would be proportional to the diffusion current in the emitter by electron. Okay, but this slope can be well estimated as a tangent line, the slope of the tangent at x2 prime of 0. And the proportionality coefficient is defined as unit charge of electron times cross-sectional area of P and PJT and the diffusion constant in the emitter. Okay, so go back to the diffusion current. Diffusion current is defined as unit charge times diffusion constant times doping concentration gradient. If you're not familiar with the definition of diffusion current, go back to the diffusion part, chapter 3.2, and review it, and come back to this slide again. Okay, so the things complicated is this: E, N, E, 2 prime stuff, E. Just remove all the subscript, then you'd be more familiar. Okay, please do that. All right, now let's move on to the I sub EP. By hole in the emitter, how much current has been formed? Well, definitely by diffusion mechanism. So, unit charge, cross-sectional area, diffusion constant times how much doping concentration gradient has been formed at the depletion region edge. Okay, so in the base region, the minor carrier hole access, the slope, doping concentration gradient. I mean this right slope, this slope. Okay, since we have know the delta p sub b as a function of x, so this slope is this. Okay, then the proportionality coefficient is this. Then you're gonna end up with the I sub EP. This I sub EP was used to define, emitter efficiency gamma. Gamma is IEP, right? So this IEP is IEP plus IEN. So now we are ready. IEP is this, and IEN is this. So to know the IE and IEP, or to know the emitter efficiency, we should have the equation for IEP and IEN. The core part is this doping concentration gradient. Okay, and this doping concentration gradient has been achieved and implemented because of this fold bias between emitter and base. Okay, all right, and now it's time to derive the equation for collector current by electron and another collector current by hole. Since this collector junction, I mean the collector base junction is reverse biased, so saturation, a very tiny amount of current has been formed, but not negligible. So take a look at this excess carrier profile along x direction or x prime direction. There is doping concentration gradient, so that ICN, ICP should not be 0. Okay, so doping concentration gradient happened here and there. I mean at the depletion region edge, x prime of 0 and x of w. Okay, all right. I mean the x prime of 0 is where? Yeah, here. This depletion region edge, and I sub cn means this slope. Okay, delta and c. So delta and c, the first order derivative of delta n sub c at x prime of 0 would determine the I sub cn. What about here? Delta p sub b as a function of x at the edge of the collector junction, I mean the x of w, would determine the I sub cp. Okay, so in the step number 2, we have what? Yes, we have IEN, IEP, and ICN and ICP. So since, let me erase my note. So here IE is IEP plus IEN, and here IC is ICP plus ICN, and this is base current. So IE is equal to IB plus IC. So the last sentence indicates that hole component, electron component, the emitter current by hole, emitter current by electron, if I add two terms together, then we're gonna get the emitter current, which is terminal current. Okay? And similarly, if I draw the right equation for collector current by hole and another right equation for collector current by electron, then if I sum them up, then I'm gonna get the collector current, which is another terminal current. So once I know the two terminal currents in PNP BJT, then the last terminal current, which is a base current, can be simply obtained using this equation. So we almost done, okay? So from now on, we're gonna split single BJT into three different regions: emitter region, collector region, and base region. So let's take a look at briefly one by one. Emitter region analysis. So in the PN, maybe another P as a collector, right? But we don't care about the collector side at this moment. Why is that? Because we are talking about the emitter region, emitter current, IEN, here, IEN first. So in the previous lecture note, I have derived this simple equation, but how to get this? So more details are introduced here. So let's take a look at it. But before taking a look at it, let's move on to the next one. So this slide indicates emitter region analysis. And now let's move on to the collector region analysis. Again here, take a look at maybe emitter side P plus and base and collector P, but we don't take too much care on emitter side. The collector side is the things that we are very interested in. So I sub C n, the collector current by electrons, maybe the base electrons would be diffused into the P side, but this is reverse biased junction, so maybe this electron injection would be negligible. But anyhow, we're gonna use minority carrier diffusion equation for this quasi-neutral p-type region, which is a collector. So again, minority carrier diffusion equation and the boundary condition stuff, and in the end, we're gonna get this equation. So we're gonna do that. All right. The last part in BJT is base, right? So in this base regime, we're gonna solve the minority carrier diffusion equation again, and using boundary condition, we're gonna solve how much holes, excess holes, are obtained in the base region as a function of x. X indicates this direction. Okay. Previously, I have write down delta p sub b as a x that would be drawn like a first order polynomial equation. This analysis has been done already when we are learning the narrow base p-n junction diode theory. Okay, so hyper stuff has been back again. Okay, so once this emitter side, base region analysis, collector region analysis, emitter region analysis, if we have finished those three separated step analysis, then we are going to combine each terminal current. So from those three slice, this part, base region analysis, and collector region analysis, and emitter region analysis. Once we have finished those three analysis, we're gonna combine those current component, and then we're gonna write down the equation for emitter current, collector current. Okay, it looks like a very complicated, but don't be afraid too much. Everything, all the complicated equations, terms, we have already learned it. Afterwards, we're going to study the BJT with narrow base and go back to emitter efficiency, base transport factor, common base DC current gain, common emitter DC current gain stuff. Well, gamma times alpha t is identical to the alpha dc, and this beta dc is alpha dc divided by 1 minus alpha dc. We know this relation, but this relation has been well spread out and widened out with many device parameters such as base width, diffusion length, doping concentration in base emitter, and collector region stuff. Okay, so I guess I have spent too much time, but in the upcoming movie clip, I'm going to begin with emitter region analysis. But before moving forward, I have briefly debrief what we are going to learn. Okay, so in your mind, please have your own strategy and game plan. How to approach, how to get the current voltage characteristic of your own BJT. For that purpose, the very first step is we should solve the minority carrier diffusion equation in each quasi-neutral region. In emitter, in the base, or in the collector. Afterwards, we are going to find out the minority carrier diffusion current at depletion region H. The extra prime of 0, x is 0, x is W, and x prime is 0. Afterwards, we're gonna sum up whole current component, electron current component for each terminal. And then we're gonna end up with the emitter current, collector current. So this whole process is very important and significant in understanding the game plan for IV derivation for your BJT device. So please preview this time, this analysis and that analysis, in the end the base region analysis. Actually, those are three analyses we have already learned it, but take a look at it first, and then take my next movie clip. Okay? All right, that's all for today's movie clip, and see you in the next movie clip. Bye bye. Thanks for your attention. See you in the next movie clip.